Hey students, I got a good question by email here during Zoom hours. Let me make a solution to number 53, but also let me use it as a chance to kind of lecture again, because this chapter on kinematics has these 5 equations. Let me just write them again. We call this equation 1. Equation 2 has to do with position. Equation 3 is when we solve this for time and put it into here. Equation 4 is when we solve this for A and put it into the second one. And equation 5 is when we solve this for initial velocity and put it into here. And what I wanted to start off on this problem is just to remind you that there are really 5 different variables here. You can see the final velocity, you can see initial velocity, you can see acceleration, and you can see time. So these are the 4 in here. Another one, though, and I want you to think of it as one variable, is the difference between x minus x naught. You might even call it delta x, but it's basically meaning how far did it move, and so this is the displacement of it. And so maybe we don't need to know the individual positions, because that really is based upon where you put your origin. But here's what I'm trying to say. I bet that if you ever have a constant acceleration problem, and so let me emphasize, if you don't have a constant acceleration, you need to go back to your calculus. But in a constant acceleration problem, what will probably happen is they will give you 3 of these. You will then be asked for a 4th one, and they will say nothing about the 5th one. And that's how you kind of decide which of these ones to use, which one is not included and not being asked for, because you don't need to solve for it, so you don't want it part of the equation. And you're not given it, so again, you don't want it part of the equation. And so it's better to look at each of these and say, what variable is not in this equation? So this first one would be the distance traveled. The second one here would be final velocity. The third one would be time. The 4th one would be acceleration. And the 5th one would be initial velocity. And so this is kind of how we're going to approach this problem. And probably every problem. So maybe I'll keep this around as I make more solutions. All right, so now let's actually get to the question at hand, number 53. So 53 says that there is a 250-meter high cliff at Half Dome in Yosemite National Park in California. Suppose that a boulder breaks loose from the top of the cliff. How fast will it be going when it strikes the ground? All right, now here's one of those problems where we want to be a little careful on which way we call positive and which way we call negative. Since the traditional is to call up positive, that tends to be a little more comfortable with students, so I will follow that suit. However, I must admit, since it is falling, I'm kind of tempted to just label down as positive, and I won't have to deal with negative numbers. But I think you might feel more comfortable if I don't do that. So I'm going to go to the standard tradition and call up positive. And I'm going to just make and recommend you make a little list here of velocity, initial velocity, acceleration, time, and distance traveled. And then C which of the three they give you, which of the ones they are asking for, and so which is the one missing completely from the problem, the one not being asked for to solve. All right, so this first part of it says there is a 250 meter cliff. And then it says, of course, suppose a boulder breaks loose from the top of this cliff. And then the question A is how fast will it be going when it strikes the ground? So I'm going to say that they are actually giving me the distance traveled. They're saying this boulder is going to fall downward. And since it's downward, the change in position would be negative. And so I'm going to put a negative 250. So that's clearly given. Now, indirectly given, but still given, is right here the initial speed. It breaks off. So it was at rest, and so it started with 0 speed and then, of course, started falling, and because of the acceleration due to gravity, got faster and faster. So I would say this is a given, but you got to read a little bit into the problem. So that one's maybe a little harder to get than this one. This one's pretty clear, the number, but this one's not so clear. Now, another subtlety here is that the acceleration is negative 9.8 meters per second squared, because we're talking about a falling object. And the point in this chapter, well, there were many points, but one of them was that all objects have the same acceleration of 9.8. And that's actually what we measured in lab number 2. So there it is. In fact, their answer is my first thing. Notice how they've given me 3. And what are they asking for? At least in A, it says how fast. So they're asking about this one. So I would argue that the one missing for at least part A is time. And as I come back to my thinking, equation number 3 seems like the way to go with this. So final speed squared is equal to initial speed squared plus 2 times the acceleration times the distance traveled. Okay, so I'm looking for this final speed. The initial speed is 0. As we just mentioned, the acceleration is negative 9.8 meters per second squared. And the distance traveled is a negative 200 and, what do we say here? 250. Oh, I didn't put it meters. Let me just check. Is it meters? Yeah, 250 meters. And so, if I do this first calculation, I would go 2 times negative 9.8 times a negative 250, and that is 4,900. So when I take this square root, it'll be plus or minus, and then you can see this is 49 times 100, and so square root of 49 is 7, square root of 100 is 10, and so this would be 70 meters per second, now plus or minus. So the math works out as plus or minus because whether you would have called down positive or negative, it should come out to be the same thing. Since I was calling down negative, to be consistent with that, I'll pick the negative one as the correct one, and so there is the speed at the bottom. I guess its speed is 70, but it's downward and hence the negative. All right, now in B, it goes on to say, assuming that a reaction time of 0.3 seconds, how long would a tourist at the bottom have to get out of the way after hearing the sound of the rock break loose, neglecting the height of the tourist, which would become negligible anyways at this speed. The speed of sound is about 335 meters per second on this day. All right. So let's see. It said, assuming reaction time of 0.3, how long will a tourist at the bottom have to get out of the way after hearing the sound? Okay, so if I were to draw the top of the cliff like this and say, okay, it breaks away, and then sound travels down, let's see when the tourist is going to hear it. So at this point, I'm talking about the speed and the motion of the sound, not the rock itself. I want to go back and talk about the rock, but let's just talk about the sound. And let me maybe even write out what we have. We have the 5 variables. And this is not quite as clear. We haven't really talked too much about sound, but they are saying, when they say the speed of sound is 335 meters per second, what they're saying here is that's the speed all the time. It's the speed at the top, the speed at the bottom, the speed in the middle. So this, in other words, the speed doesn't change. It doesn't accelerate. It's not like the falling rock. And so they have just said indirectly that the acceleration is 0. They are saying that you don't change your speed. Which means, of course, the initial speed of sound, 335, is the same as the final speed of the sound. There is no change. It just keeps having the same speed. And so when final and initial are the same, there being no change would mean the acceleration is 0. Now, again, oh, and I guess I better put negative. The sound's going down, so I want to be consistent here and call down negative, okay? Also, the sound does have to go down the cliff. So the down is the negative, and it's, the 250. That's what we said for the rock and red in part A. So again, notice that for the sound, they have given me actually 4 and asking me to solve for this. So I could actually then use any equation. There isn't anything here missing. So I can use any equation, I guess, at least as long as it has time in it. So I guess technically I could use this one, but that won't get me anywhere. You'll kind of see that. I'll put in 335 here, 335 here, but 0 here. And so I just get 335, or actually negative 335 and negative 335. So technically I could use that equation, but it really won't help me because the A is a 0, and so the time would go away. Bummer. How about this one here? This is the time traveled, or excuse me, distance traveled. Initial velocity I know, and then the time. This is looking good. In fact, it looks even better because this one would go away because A would be 0. And I like that one. I guess I could also do this one. I guess I could also do that one. But all 3 of these really are the same thing at this point once you put A equals to 0. So I only skipped number 3 because it's the only one that doesn't have time in it. But why don't I just do number 2 and say, okay, x minus x naught equal to initial velocity times time plus 1/2 at squared. And as I said, this is going down, so that's the negative 250 meters. The initial speed is the negative 335. That's also the final speed because there's no acceleration, which then gets me to this point. That's a 0, no acceleration. So when I solve this for time, I guess the 2 negatives would cancel off. Even a meter would cancel off. And when you bring this over, seconds in the bottom of the bottom, so in the denominator of the denominator, would flip over and you would get seconds. And so grabbing my calculator, 250 divided by 335 is roughly 3/4 of a second. Okay. So keep that in mind that this is you, or a tourist down at the bottom, isn't even going to hear the breaking of the rock until about 3/4 of a second. So the rock's already been falling for a while. And so let me split this and over here say, well, what about the time for the rock to fall? Well, this brings me back to A. As you know, we were giving 3 things, and we even then calculated a 4th one. And I would say then we know 4 of the 5. We're kind of back to the statement we did for the sound waves, that you could use any of the equations that have time in it. Now, in this case, why don't I stay away from equation 2, and for that matter, equation 5. They do have time in it, but it's quadratic. Although, now that I say that, this second one wouldn't be so bad because this would be a 0, and so I don't have to do a quadratic formula. I just have to take a square root. So I don't think that's so bad, but hey, I would much rather just take a square root than do a quadratic formula. However, I'd prefer not even to have to take a square root. So let me hold off on that one, because I can see if I did number 4. I know these things, and I can just then calculate the time. So that's the one I'm liking. I don't like number 5 at all, because I'd have to number here, and I would have then a time here, and I would have a quadratic. And sure, it'll work, but I have to solve a quadratic. Now, with all that said, I also like number 1, initial speed and final speed of the rock, acceleration and time, because that is, no square roots or quadratic. So both number 1 and number 4 look very promising to me. But I'll point out, I can use any of them that have time in them because we know 4 of them. Okay? And that's because we already did part A. So I'm going to pick the easiest one, which I think is just number 1 to do, and it'll give me time. And the only one I couldn't use is number 3, because it doesn't have time in there. So there's no way you can solve for time without it being in the equation. So that's why we are looking at what's not in the equation. All right, so let me just use the equation number 1 here. So this would say for the rock, the final velocity equals the initial velocity plus acceleration times time. And the final velocity is the negative 70 meters per second that we worked out in part A. The initial speed of the rock, as it breaks off, that's the 0. The acceleration is the negative 9.8 meters per second squared. And then the only unknown is time, and I can solve for it. And of course, looking closely at this equation, this 0 goes away. You got a negative on each side, so those will cancel off. You have a meter on each side, that'll cancel off. You have a per second, which goes with a per second, so there's 1 per second left over, which you're going to move underneath, and so this is going to be the denominator of the denominator, which flips and puts it upstairs when you do your flip and multiply, so that's seconds. So this would be then the 70 divided by 9.8. So 70 divided by 9.8 is 7.14. 7.14 seconds. So that's how long it's going to take for this rock to fall. Clearly a longer time than the sound to get to you. Okay? But like you said, you don't have this full 7 seconds, because by the time you hear it, 3/4 of a second has already elapsed. Okay? Also, keeping in mind you have what you call a reaction time. So when you hear it, which is a little delay, then you kind of go, oh, gotta move. Your legs start to move, and so let me add a reaction time. They gave us a good number. What number did they give us for reaction? 0.3 seconds. So I would say, because of the time it takes for the sound to get down to you and your reaction time, you're not going to actually move until 1.048 seconds. Roughly 1 second before your body actually starts to move. So you have, how long will a tourist at the bottom have to get out of the way after hearing the sound of the rock breaking loose? Depending on their meaning, you would take this minus that to say how much time do you have after hearing it. That's when you hear it. But I think they want you to include your reaction time, because your reaction time is then saying, okay, your body has now made a decision. Your body has heard the sound. Your body has recognized the sound. Your body is now saying, get out of the way. And so the time you really have to move is the difference in this. And of course, if it's a big boulder falling at this great height, it's probably going to hit and shatter. So you're going to want this whole time to get out of the way. And I think that's what they're trying to say here. How long will the tourist at the bottom have to get out of the way, the way of the shattering debris? And so this is the 7.14 minus 1.046, coming up with roughly 6.09 seconds. So once your body starts moving here, so that's after your reaction time, how far can you move in 6 seconds is really going to be how far you're out of the way, assuming it was heading straight towards you. And they don't really talk about that. I just think they wanted to kind of make us think about the sound coming down and the rock coming down and the difference between them. All right, there's a problem. Hopefully that was useful. Take care.